Hello. This is a recording for those who are absent today. I'm not sure what today's date is, but it's Wednesday, chapel day, and this is the physics class. So welcome to those. I meant to videotape this during class and totally forgot. So I'm just going to do a short rendition at home, and I'll put this up for you so you'll know what you missed during class. First of all, I'm just going to tell you that we worked on the lab, so if you need to do any further calculations, then you need to do those at home. If you actually need the force table to finish something, you'll need to see me and spend a few minutes with that. So we took about 10 minutes to share the rest of our calculations with one another and finish up getting any data that was needed, so that's all taken care of. So that lab is due this week. Tomorrow will be great, but if you're not able to because of your absence, Friday's fine. So, and we mentioned that there's a test next Thursday, and that is wherever we are in this mod, we're going to stop and have the test. So if we're not quite finished, we'll have another mini test later to finish it up. Behind me on the board are some definitions, so I'm just going to read them quickly to you, and you will stop the video and write them down. So I will not pause for you to do that, as I am trying to not use up so much video time. I get 10 minutes and then another 10-minute block. So here we go. Get out of your way. Definitions. The first definition is translational movement, and that translational movement is what we've been studying so far. It's from point A to point B in a straight line. We can go horizontally, right and left, we can go vertically, and now we go diagonally. So we've studied that kind of movement. Then today is our new type of motion. It's rotational. So we're going to go around the center point, and we call that center point the axis of rotation, and we'll see that in a minute again. And the force that causes all rotational movement is called torque. Torque is the new force that we're studying today. T-O-R-Q-U-E, pronounced torque. Now, I have an example here where torque is involved. If you would sketch a wrench around a bolt, and the center is the axis of rotation, and the distance from the center to where the force is applied, that is called the lever arm. And here it is written in words. The lever arm is the length of an imaginary line from the axis of rotation to where the force is applied. So you can go ahead and get that down. I'm going to erase it, but you can pause the video and get that. So a little bit about torque. Torque has a formula and a symbol. The symbol for torque is a T with a wavy hat, and its formula is force applied perpendicularly times the radius. Notice that torque is describing circular motion. Did you notice that the wrench, when you push down on here, and it's on this bolt here, it will cause the end of the wrench to go in a circular pattern. So there is a force involved, and the only force that counts is the force that is applied perpendicularly to the lever arm, and it causes circular motion. And R is the radius or the length of the lever arm. The distance from the center, also called the axis of rotation, to where the force is applied. That is the radius or the lever arm. What are the units for torque? we can tell the units for torque by looking at the equation. Force is in newtons, radius is a length, so it's meters. So there is the unit for torque, Newton meters. And in America, we would call a Newton a pound, and we would measure a meter in feet. So in the US, we often use the word foot-pounds, and you may have heard of that. Foot-pounds, that's LB. They're standing for pounds. All right. In addition, we covered a new term called rotational equilibrium. But before I get to that, let me do one more thing with the wrench. Because we have a wrench, let's say our wrench is 6 inches long. That means it's the same as a 15.2 centimeters long. 15.2 centimeters. And suppose that my force that I apply is 653 newtons. What is the torque? Well, the torque is going to be the force, which is 653. I'll drop the units, you know it's newtons, times the radius. If I want to come out in Newton meters, I have to switch that to meters. So it's 0.152 meters. So someone in class multiplied that out for us today and got 99 point something 3 Newton meters. But guess what? The bolt did not move, not one bit did it budge. And I can press no more than the force of 653 newtons. So we said, well, what if we change the lever arm and we get a longer wrench? So 15.2 is 30.4 now centimeters, or 0.304 meters. Now if I calculate the torque this time, it's still 653 newtons times 0.304 meters. And when someone tapped that in, they got 199 Newton meters. Look at the difference. Now the bolt moves with ease. So without any more force, I was able to find more torque by increasing the length of the lever arm. In other words, getting a longer wrench. And perhaps you've noticed that that has been true in your experience. All right. Again, you can pause and get this material if you need to. We ended up discussing something called rotational. That's not rotational. Now move it over here. Rotational equilibrium. Just like in translational equilibrium, if you look at the first part of our mod, we started out with definitions regarding translational equilibrium. It involves two things. It can either be still, it's not moving in a circle, or it can be moving with a constant velocity. In either one of these, the acceleration is the same. What is it? Acceleration here is 0 and here. So in both of these rotational equilibrium, an object is in rotational equilibrium, the acceleration is 0. They're either still or moving with a constant velocity. We have a name, just like we did with translational equilibrium. And when it's still, it's called static equilibrium. I'm just abbreviating the equilibrium. And over here it's dynamic. Okay, that's a timer. I just have to stop the recording and start it again. So just hold on.